I've watched it happen at least 2 dozen times. A family brings home their first 3D printer, tears open the box with all the excitement in the world, plugs it in, loads up a file, and then nothing. Or worse, something prints, but it's a mess. Turns out, a 3D printer by itself is just one piece of a much bigger puzzle. I'm Kazuki Tanaka, and I've built 11 of these stations from scratch across community makerspaces and home workshops. Today, I'm walking you through everything you actually need to get it right the first time. You're listening to the STEM Lab podcast. Quick thing before we get going. The research, the data, all the script work, that's done by real people, fully human verified. The voice you're hearing now, though, that's AI generated. Just want to be upfront about that. If you've been listening for a while, thank you. Genuinely, it's great to have you back. And if you're new here, welcome aboard. We drop new episodes every Monday, Wednesday, and Friday, covering STEM education tools, projects, and setups. Today we're talking about 3D printing stations for kids, and I'm breaking down the entire checklist so you don't waste money or end up missing something critical. Let's jump in. Here's what you're really looking at. Somewhere between $400 and $900 for the initial investment if you include the printer, and then expect to spend $20 to $30 a month on filament if your kid is actively printing. But when you do this right, you're not just buying a gadget, you're building CAD fluency, spatial reasoning, and iterative problem-solving skills that translate directly into mechanical engineering, product design, and industrial manufacturing careers. I know exactly where beginners waste money and where cutting corners just creates frustration, so let me save you both. Now, let's talk about what to actually look for when you're setting up one of these stations. You need to start with safety and the environment itself, not the printer. First thing, you need active ventilation, either a dedicated fume extractor or a window with a fan that's rated for at least 100 CFM. Even PLA, which is corn-based and gets marketed as safe, emits ultra-fine particles while it's printing. ABS releases styrene, and you absolutely do not want kids breathing that for hours. I install a simple 6-inch inline duct fan in every workshop I set up. Costs about $40, and it makes a measurable difference on my air quality monitor. Temperature control matters more than most guides will tell you. Your printing area needs to stay between 65 and 80 degrees Fahrenheit with minimal drafts. I've tested this extensively. Prints fail when an AC vent blows directly on the build plate, and kids get discouraged when their 4-hour print warps at hour 3 because someone opened a window. Use a room thermometer and pay attention to how things change with the seasons. Fire safety is non-negotiable. Keep a Type ABC fire extinguisher within 10 feet of the printer. I've seen 2 printer fires in my career, both from worn power supplies, and having that extinguisher within arm's reach is the difference between a scary story and an actual disaster. Add a smoke detector directly above the printing area, not across the room. Moving on to the hardware itself. The big decision here is enclosed versus open frame, and it drives everything else about your setup. Enclosed printers contain heat better, they reduce particle exposure, and they prevent kids from touching hot components mid-print. Open frame printers let you watch the process clearly, they teach troubleshooting more effectively, and they cost 30 to 40% less for similar print quality. I recommend enclosed designs for kids under 12 or households with curious pets. The FlashForge Adventurer 5M Pro hits the sweet spot. It's got built-in HEPA filtration, a fully enclosed heated chamber, auto bed leveling, and cloud-free operation via USB or local Wi-Fi. For teens who are ready to learn bed leveling and maintenance, open frame options like the Creality Ender 3v3 teach more about the actual mechanics. Here's what you need to verify before you buy. Auto bed leveling saves about 80% of beginner frustration. Resume printing after power loss protects those 8-hour overnight prints. A heated build plate that reaches at least 100 degrees Celsius is required if you ever want to print PETG or ABS.
Connectivity options matter too. Local file transfer beats cloud-dependent systems that break when servers go down. And build volume should be at least 220 by 220 by 250 millimeters for most educational projects. Next up, design software and the learning progression. Your checklist has to include CAD software paths from beginner tools to industry standard ones. I start every student on Tinkercad. It's free, browser-based, works on Chromebooks, tablets, any OS. They stay there for 2 to 4 weeks until they're comfortable with 3D manipulation. Then we jump to Fusion 360 for students, which is a free educational license but Windows and Mac only, and it requires annual verification. Tinkercad teaches constructive solid geometry, which is adding and subtracting basic shapes. Fusion 360 teaches parametric modeling, which is defining dimensions and relationships that update throughout a design. That second skill is what mechanical engineers use every single day. Slicing software is what translates CAD designs into printer instructions. Use the manufacturer's recommended slicer first. It's often proprietary and simplified, which is good when you're starting out. Then graduate to Cura, which is open source, supports over 400 printer models, and runs on Windows, Mac, and Linux. Kids need to understand infill density, layer height, support structures, and print orientation. These are what determine whether a design actually succeeds or just fails halfway through. Let's talk materials, storage, and consumables. Filament is your ongoing cost. Plan on $20 to $25 per kilogram of PLA, and typical educational projects consume 1 to 2 kilograms monthly during active use. Store filament in airtight containers with desiccant packs. I use 5-gallon buckets with gamma lids and rechargeable silica gel packets. Moisture absorption ruins filament quality. It causes brittle layers and stringing defects. Start with PLA exclusively. It prints at lower temperatures, 190 to 220 Celsius versus 230 to 260 for ABS. It doesn't require an enclosure, and it produces way less hazardous emissions. Once your student masters bed adhesion, layer adhesion, and support removal, then you can consider PETG for strength or TPU for flexible parts.
Here are the consumables you'll replace regularly. Build surface sheets every 50 to 100 prints, around 15 to 20 bucks. Nozzles every 200 to 500 hours, around $8 for a 5-pack. PTFE tubing annually, around $10. And isopropyl alcohol for bed cleaning, ongoing. I recommend buying that in bulk. Now we get to the toolkit and finishing equipment. This is where I see the biggest gaps in beginner setups. You need post-processing tools to turn rough prints into functional parts. Flush cutters for removing support material and brims. Get the sharp-pointed ones, around $12. Needle files. A 6-piece set covers 90% of finishing needs, around 15 bucks. A deburring tool for cleaning holes and edges, around $8. Digital calipers for measuring printed accuracy. I use the Nico 01407A, around $18, and it teaches precision measurement. A spatula or scraper with a thin, flexible blade for print removal. The one that comes in the box usually breaks, so get a metal one, around $10. I also keep a heat gun, around 25 bucks, for smoothing PLA surfaces, and a small rotary tool with sanding attachments. Safety glasses are mandatory for support removal because snipped support material flies unpredictably. Let me walk you through what capability progression actually looks like. Month 1 to 2, your kid successfully prints pre-designed models from Thingiverse, understands bed leveling and adhesion, and can remove prints without damage. Month 3 to 4, they design simple custom objects in Tinkercad, like keychains, boxes, brackets. They modify existing designs and understand basic slicing settings. Months 5 to 8, they create parametric designs in Fusion 360, print functional assemblies with moving parts, and troubleshoot failed prints independently. Month 9 to 12, they design products with specific mechanical requirements, incorporate threaded inserts and fasteners, and produce parts accurate to plus or minus 0.2 millimeter tolerances. That final milestone is where you're building actual industrial design skills. I've had students create replacement parts for broken appliances, custom cases for electronics projects, and prototype designs that eventually got manufactured. So here are my top picks for the components you actually need. The FlashForge Adventurer 5M Pro is my top recommendation for educational environments. It's fully enclosed with active carbon and HEPA filtration, auto bed leveling that actually works, and a heated chamber that maintains temperature stability. I've run this printer through over 300 hours across 6 months in my workshop, and it delivers consistent first layer adhesion with minimal tweaking. What I like about it, the built-in air filtration reduces particle exposure by 70 to 80% in my testing. Resume printing after power loss saved a dozen overnight prints during winter storms. The magnetic flexible build plate removes without damaging prints. 280 by 280 by 280 millimeter build volume handles larger educational projects. Direct drive extruder improves filament control versus Bowden systems. The touchscreen interface has clear graphics, so you don't need a computer for basic printing. And local Wi-Fi transfer works without mandatory cloud accounts. What I don't like, the proprietary slicing software limits advanced customization. It works with Cura, but you need to tweak the profile. It's heavier than most beginner printers at 38 pounds, so it's not easily portable between rooms. And replacement nozzles are FlashForge specific and cost more than generic alternatives. You're looking at 110-volt AC power, 300-watt peak consumption, USB, Wi-Fi, and Ethernet connectivity. It comes with a 0.4mm nozzle standard, but you can get 0.2 and 0.6mm sizes. It prints PLA, PETG, ABS, and TPU. Build plate heats to 100 degrees Celsius. You need 20 by 20 inches of desk space. Check the link below to see the current price. The Creality Ender 3 V3 SE teaches the mechanics of FDM printing better than any enclosed system. The open frame design lets students see every movement, and manual bed tramming builds troubleshooting skills. They call it leveling, but it's really tramming. I keep 2 of these in my community makerspace because they're repairable, upgradable, and they force users to understand what's actually happening. What I like? It's around $200, which makes it accessible for most families. The CR Touch Auto Bed Leveling reduces beginner frustration, and that's a huge improvement over the original Ender 3. Open frame design teaches printer mechanics and failure modes clearly. There's a massive online community and upgrade ecosystem, so replacement parts ship next day. Direct drive extruder improves flexible filament printing. It prints 250 millimeters per second maximum, which is twice as fast as the previous generation, and it's compatible with Cura, Prusa Slicer, Simplify 3D, and most slicing software. What I don't like, there's no enclosure, so ABS printing is difficult without modifications. The PEI build surface requires regular cleaning and eventual replacement. The Bowden tube connector loosens over time. I replace mine every 150 hours. And the manual filament runout sensor requires user intervention.
Specs: 110-volt AC power, 350-watt peak, USB-C and micro SD connectivity, 0.4mm nozzle standard. It prints PLA, PETG, and TPU. 220 by 220 by 250 millimeter build volume. Heated bed goes to 100 degrees Celsius, weighs 15 pounds, requires assembly about 30 to 45 minutes with included tools. Check the link below to see the current price. Overture PLA Pro filament is my go-to recommendation for educational printing. It's got consistent diameter tolerance, plus or minus 0.03 millimeters in my measurements, minimal moisture absorption in storage, predictable interlayer adhesion across over 20 spools I've tested. The 6-color variety pack gives students experience with bed adhesion differences between pigments. What I like? Vacuum-sealed packaging with desiccant maintains dry storage during shipping. It prints reliably at 200 to 215 Celsius across different printer models. Matte finish hides layer lines better than glossy PLA. Stronger layer adhesion than standard PLA, which is important for functional parts. Color variety encourages multi-material design thinking, and the cardboard spools are recyclable, which is better than plastic alternatives. What I don't like? It's slightly more brittle than some premium PLAs when printing fine details. Color consistency varies slightly between production batches, and there's no resealable packaging, so transfer it to airtight containers immediately. Specs: 1.75 millimeter diameter, plus or minus 0.03 millimeters, 1 kilogram spools, Prints at 190 to 220 Celsius. Bed temperature 50 to 60 Celsius. Storage in a sealed container with desiccant required. Shelf life 12 to 18 months when properly stored. Check the link below to see the current price. The Sunlu Filadryer S2 solved my biggest filament quality issue, which is moisture absorption that causes stringing, layer separation, and brittle prints. This dryer holds 2 spools simultaneously, maintains 45 to 55 degrees Celsius drying temperature, and includes integrated rollers that let filament feed directly from the dryer to your printer during printing. What I like? Dual spool capacity means you can prep tomorrow's filament while printing today's project. Integrated rollers reduce friction compared to feeding from separate dry boxes. Digital temperature display, not just preset buttons. It runs quietly. I measured 38 decibels at 3 feet, which is quieter than most printers. Collapsible design stores efficiently when not in use, and it's compatible with 0.5 kilogram to 3 kilogram spools.
What I don't like: the power cord is only 4 feet long, so you need an extension cord for most workbench setups. Temperature maxes at 55 Celsius, which is insufficient for nylon or other engineering filaments. And the transparent cover scratches easily after 6 months of workshop use. Specs: 110-volt AC, 70-watt power consumption, timer up to 24 hours, holds 2 1-kilogram spools or 1 3-kilogram spool. Dimensions 9 by 8 by 7 inches collapsed. Compatible with 1.75 millimeter and 2.85 millimeter filament. Check the link below to see the current price. The iFixit Essential Electronics Toolkit isn't marketed for 3D printing, but it's my #1 recommendation for maintenance and post-processing. I use these tools for nozzle changes, hot end maintenance, removing stuck prints, and cleaning extruder gears, all regular tasks in any printing station. What I like: the precision screwdriver set covers every fastener size on modern 3D printers. Spudger tools remove prints without damaging build surfaces. ESD-safe components protect printer electronics during maintenance. Tweezers in 3 styles handle support material removal effectively. The carrying case keeps tools organized, which is critical in shared workshop spaces. And there's a lifetime warranty on tools. I've replaced 2 worn drivers under warranty. What I don't like: some drivers are too short for reaching recessed printer screws. I supplement with longer alternatives. The case zipper weakened after 2 years of daily workshop use. And it doesn't include the larger hex keys needed for frame adjustments. It's a 64-piece set, magnetized driver tips, opening tools rated for plastic and metal. Tweezers are ESD safe. Carrying case 9 by 5 by 2 inches. Tools manufactured to ISO 2380 standards. Check the link below to see the current price. The Nico 01407A digital caliper teaches precision measurement and quality control, which are skills that separate hobbyists from engineers. I require every student to measure their first 10 prints and compare their dimensions to their CAD designs. This 6-inch caliper reads to 0.01 millimeter resolution and handles 90% of educational measurement needs. What I like: instant zero setting at any position, which is critical for measuring print accuracy. It switches between metric and imperial instantly, which teaches unit conversion. Depth gauge reaches into recessed features and holes. Step measurement function for checking layer heights and feature depths. Durable stainless steel construction survives workshop drops. And at around $18, it's affordable for every student workstation. What I don't like: the battery compartment cover loosens after 200 to 300 battery changes. I just tape it closed. Digital display isn't backlit, so it's difficult to read in dim workshop lighting. And it needs recalibration against gauge blocks every 6 months for precision work. Specs: 0 to 150 millimeters or 0 to 6 inch range, 0.01 millimeter / 0.0005 inch resolution, Accuracy plus or minus 0.02 millimeters. Powered by CR2032 battery. Auto off after 5 minutes. Supplied with a protective case. Check the link below to see the current price. Let me answer some of the most common questions I get about setting up these stations. What age is appropriate to start using a 3D printing station? Kids can start observing and designing for 3D printing around age 7, with hands-on printer operation appropriate from age 10 to 12 with supervision. The limiting factor isn't intellectual understanding, spatial reasoning develops earlier. It's really about safety awareness around heated components and the patience required for multi-hour print times. I've taught 8-year-olds to design in Tinkercad successfully, but they need adult supervision when operating the actual printer, especially during filament loading and print removal. By age 14 or 15, most teens can operate the entire workflow independently after initial training. The key skill progression is design software first, which is purely digital and zero risk, then supervised printing, then independent operation. Do I need a dedicated room for a kid's 3D printing station? You don't need a separate room, but you need dedicated space that meets ventilation and safety requirements. I've set up successful printing stations in basement corners, garage workbenches, and spare bedroom areas. What matters is active air movement, either a fan to a window or a fume extractor, fire safety equipment within reach, and enough space that curious siblings or pets can't access hot components mid-print. The minimum functional footprint is about 3 by 3 feet for the printer, filament storage, basic tools, and a laptop or tablet for slicing. You'll expand to 4 by 6 feet once you add finishing tools, failed print collection, and project storage. Noise is a consideration. Most printers generate 45 to 55 decibels during printing, similar to a quiet conversation, but 8-hour overnight prints might disturb light sleepers if the station is in an adjacent bedroom. Temperature stability matters more than square footage. How much does filament cost and how long does it last? Plan on around $20 to $25 per kilogram of PLA filament, with a typical 1 kilogram spool lasting 4 to 8 weeks for moderate educational use. That's 2 to 3 prints weekly. Small projects like keychains or fidget toys use 5 to 15 grams each, while functional parts like phone stands or brackets consume 30 to 80 grams. A 1 kilogram spool contains enough material for roughly 400 meters of filament at 1.75 millimeter diameter. That translates to about 15 to 25 typical student projects before replacement. I budget $30 to $40 monthly for filament in an active single student setup, less if you're only printing occasionally. Failed prints increase consumption. Expect a 20 to 30% failure rate during the first month of learning, dropping to 5 to 10% once bed adhesion and support generation skills develop. Buy filament in bulk to reduce per unit costs, but only if you have proper storage with desiccant. Moisture-damaged filament wastes more money than buying fresh single spools. And consider different colors educational tools themselves. Switching between materials teaches students that pigments affect bed adhesion and layer bonding characteristics. Can 3D printers use the same files as laser cutters or CNC machines? No. Each digital fabrication tool uses different file formats that require specific preparation. 3D printers use STL, OBJ, or 3MF files that define three-dimensional surfaces. Laser cutters use SVG, DXF, or AI files that define two-dimensional cut paths, and CNC routers use G-code generated from different CAM software. However, the design thinking skills transfer completely. Understanding material constraints, toolpath planning, and dimensional accuracy applies across all digital manufacturing. I teach students to design in Fusion 360 because it can export for all three processes. 3D printer by exporting STL from 3D bodies, laser cutter by exporting DXF from sketches, and CNC through its integrated CAM workspace that generates toolpaths. This workflow mirrors professional product development, where one CAD model generates manufacturing instructions for multiple fabrication methods.
The conceptual skill, designing manufacturable geometry, matters more than the specific file format.
What CAD software should kids start with for 3D printing? Start with Tinkercad for 2 to 4 weeks to build spatial reasoning and basic 3D manipulation skills. Then transition to Fusion 360 for parametric modeling that teaches professional design methodology. Tinkercad is browser-based, so it works on any device, including Chromebooks and tablets. It requires zero installation and uses an intuitive drag-and-drop interface that 7-year-olds navigate successfully. It teaches constructive solid geometry, which is combining basic shapes through addition and subtraction, but it doesn't teach parametric relationships or design intent. That's the ability to define dimensions and constraints that update automatically when you change one value. That's what Fusion 360 provides, and it's the same software used by mechanical engineers, product designers, and industrial manufacturers worldwide. Fusion 360 offers free educational licenses, requires annual school verification, runs on Windows and Mac, not Chromebooks, and it has a steeper learning curve that pays off when students start designing functional assemblies with moving parts, threaded connections, and specific tolerances. So here's the verdict. A proper kids 3D printing station setup checklist prevents the biggest beginner mistakes: buying a printer without ventilation plans, skipping measurement tools, or underestimating filament storage requirements. Focus your initial investment in 3 areas: a reliable auto-leveling printer, that's the FlashForge Adventurer 5M Pro for younger kids, Creality Ender 3 V3 SE for teens learning mechanics, proper ventilation in fire safety equipment, which is non-negotiable regardless of budget, and the CAD to print workflow, Tinkercad to Fusion 360 progression with Cura slicing software. Your station should grow with skill development. Month 1 looks like supervised printing of downloaded designs. Month 6 looks like custom parametric designs solving real household problems. Month 12 looks like functional prototypes accurate to engineering tolerances. That progression from consuming to creating to engineering builds capabilities that transfer directly into mechanical design careers, industrial manufacturing, and product development fields. I've watched this transformation in over 200 students, and it happens most reliably when the physical station supports progressive complexity rather than fighting against it.
Thanks for listening to this episode of the STEM Lab podcast. We've got new episodes coming out every Monday, Wednesday, and Friday, so there's always something fresh to dig into. If this one helped you out, I'd really appreciate it if you could leave a 5-star rating and a quick review. It actually makes a difference. It's how other people who are looking for this kind of content find the show. And if you haven't already, hit subscribe or follow so you get notified the second a new episode drops. I'll catch you in the next one.